Hi there, everyone. We're here today to look at how variables in equations are related. And specifically, we're going to get into a bit of analysis with, asking how when one changes, it affects another. So that's our goal here today. So here's our example. We have a sphere, has a radius r and a density d. We're going to take the radius of the sphere and we're going to double it. The density is cut in half. We want to know how the mass of the new sphere compares with the original. So before we get going too much with this, I want to talk at least on a conceptual level what's going on here. So the first thing is that we are increasing the radius. Now, certainly I would hope we know as we increase the radius of a sphere that that is also going to cause an increase in the volume of that object. And of course, given any object, if you make it have a larger volume, it would stand to reason that the mass should also increase as well. However, there is one little kind of setback that we have here, and that's the fact that we have this density. Of course, density and volume are related to mass. And what we're doing here, if you remember from our problem, is that density is actually going to be decreased. And as we decrease, that's going to actually cause a decrease in the mass for a given volume. So we have an increase in the volume and a decrease in the density. The big question here is how do these two effects, because they're kind of counterbalancing one another, how do they actually go together to give us our final result? Okay, so what I'd like to start with is first of all our equation for density. Density is mass divided by volume. And what I'd like to do is I'd like to get all of the, I guess we'll say, the independent variables on one side and then the dependent variable on the other side. And in our case, mass is going to be the dependent variable because we're wondering how does it change as a result of these other two things. So when I do some algebra here, I'm going to get d times v equals the mass. Okay, so in terms of our original sphere, we have the mass of that original sphere is equal to its density times its volume. Now, for our problem, let's go here a step further, and if we have a density, that's times volume. Now the volume of a sphere is 4/3 pi radius cubed. Okay, so all I've really done here is I've substituted in what was v is the volume of a sphere. And of course this is equal to the mass. Now you notice here the convenient thing about this is that this brings in the two independent variables that we have. Density, which is something that we're going to change, and radius, also something that we're going to change. So by putting these two things into our equation, we can then figure out how they affect our dependent variable. That's the mass. The next thing I'd like to do is just to do a little bit of manipulation to make this a little bit easier to see when we get our final result. We'll see what's happening here. And what I'm going to do is I'm going to pull out the things that are going to be constant. In this case, 4/3 pi is a constant. So I'm just going to put this out here in parentheses, and I'm going to have, that's going to leave me with the d times r cubed, and that's equal to mass. So again, this is just going to make this convenient because, again, this 4/3 pi is going to be constant for the first sphere and our second sphere. So I'm just going to isolate the two independent variables here, the constants here, and then of course our dependent variable there. Alright, so it should also stand to reason that for the new sphere that this same exact equation will apply. Of course, they're going to be different density, a different radius, and so forth and so on. So the way I'm going to write this is, here's our constant. There's the 4/3 pi. We'll keep that in parentheses because that's the constant. And what we're going to use here is we're going to use d prime times r prime, and that's cubed. And that's going to have to equal the new mass prime. Okay? Now a couple other notations, or another things to note here, I'm going to note these off to the side, is that remember that the radius doubles. So 2r is equal to r prime. In other words, here it says the radius, there's our original radius. If the radius of the sphere is doubled, there's twice the original radius equals the radius of our new sphere. And also, let's see here, what did it say here? The density is halved. So basically what this is saying is that the density of the new one, that's density prime, equals half the original density. So the next thing to do is substitute these into our equation over here, and we'll rewrite that. So we have 4/3 pi times d prime. Now d prime is 1/2 the original density, and we're going to substitute for r prime, and as we just said, that r prime is actually twice the original, so that's 2r cubed, and that's equal to mass prime. Alright, when I do the math, I'm going to have this 4/3, and again, one thing I could do here is, since notice how I'm rewriting this multiple times, I could just call this C for constant or something like that. It kind of seems a little ridiculous to rewrite this 4/3 pi in there, as we know it's the constant. It's in there. So, at any rate, we're going to get 1/2 d times 8r cubed, and that's equal to the mass prime. And finishing this out, there's our constant, and 1/2 times 8 actually gives us 4d r cubed equals mass prime. Now you notice here, what I'm going to do is I'm going to group this part right there, and you'll notice what that actually is. If you go back to our original, that's just the original mass. If I take the 4/3 pi times d r cubed, that gives me my original mass. So here's my 4/3 pi dr cubed. That right here is my original mass. This number right in here represents that it's actually 4 times greater for m prime. So m prime, in the end, to summarize this out, 4 times the original mass equals mass prime.